Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'd like to introduce Jim Herbslab, who's visiting today from CMU. Jim is one of the foremost researchers in the social and cognitive aspects of software engineering, and I'm really happy to have him here telling us about his latest research. And just as a note, we won't be using the left projector, so you might want to come to this side of it if you care to see the slides. So with that, here's Jim.
All right, thank you, Jan. So here's an outline of what I want to talk about today. My research over, about the last 10 years or so has been on things like geographically distributed software development teams and open source software development, trying to understand how the coordination on those projects work. And one of the things I've been trying to do recently, since I went to CMU about 4 years ago, is trying to understand more kind of the fundamental things that underlie coordination in software engineering, which has led me to an interest in fundamental things that underlie coordination in all sorts of tasks. And I'll talk more at the end about how I think from software engineering we can understand a lot about all sorts of collaborative work. So here's an outline of the things I want to talk about. Just the nature of task dependencies and coordination. I'll talk about a particular way of computing what we're calling coordination requirements. Who needs to coordinate with whom to get a particular piece of work done. And I'll talk then about some results from some empirical work that we've done, computing coordination requirements, including the volatility of those coordination requirements. How much do they change over time? Do people have to coordinate with the same people all the time, or does that change a lot? Then measuring congruence. How well do the coordination behaviors of the people involved actually match the coordination that's required? And I'll show some results that show the effects of congruence, that in fact having coordination behaviors that are congruent with the coordination requirements speeds up the development interval. I'll talk about the evolution of congruence. How does it develop over time? And in particular, I'll talk about congruence in coordination behaviors for the top performers, because the very top performers in the software development project behave in much more congruent ways than the other developers. I'll show you some data on that. And finally, I'll talk about implications for tools and for software as a service. Here, I think my idea is that software engineering produces a very rich history of a project, just by the nature of the tools that we use, change management, version control, and so on. There's a very detailed record of how the work actually gets done. For most tasks, there is no such detailed, easily accessible record, having every version of every change that everyone has done to the artifacts. With software as a service, I'm going to argue, one could design the functionality to create such a record, allowing all sorts of computations of things like coordination requirements and various collaborative capabilities. And so software engineering I see as kind of leading the way, because we've had the data first and have had time to think about what to do with it. But I think similar things could be done for all sorts of tasks where the tool is appropriately designed. So task dependencies. Task dependencies, of course, represent kind of patterns of coordination needs. People's work depends on each other's work. There's research on coordination in organizational behavior, which you may or may not be familiar with. But usually in this literature, they assume that coordination is generally falls into fairly stable patterns. And they have certain, very large distinctions among different kinds of coordination, things like pooled. Pooled is we all just do our own work, pool the results, and then, when we reach the end, we're done. Sequential, my output is your input, and so on. Reciprocal dependencies, where my output is your input, and sometimes your input is my output, and so on. But these are all pretty simple kinds of relationships. assumed to be stable. There's also literature identifying particular kinds of coordination problems that exist across many disciplines. So, for example, we can have a resource conflict. That can be true of two processes running in software. It can be true of two people who are trying to use the same resource. And the notion here is that there's a set of coordination mechanisms such that, for any kind of coordination problem, there are certain mechanisms that help to solve it. So for resource contention, we could use scheduling, for example. That's one possible way of getting around that kind of a coordination problem. So the assumption here is that there are these just stable types of coordination problems, and you can then select among mechanisms that would solve those particular kinds of problems. So there's research showing that in organizations, communication pathways kind of grow up around the most important tasks and the coordination needs around those tasks. Whose work depends on what, and that gives rise to kind of the communication channels. Okay, so in the real world, dependency patterns don't always occur in these pure stylized forms. In fact, they probably hardly ever do, except for very simple tasks. For hard intellectual, creative work, the dependency patterns are probably never easily characterized by these kinds of simple patterns that we've talked about. And also, it's pretty well known that when task dependencies change, communication and coordination may not adjust, and this failure to adjust can have dire consequences. So this next paper, Henderson and Clark, I give anyone who's interested the reference. I think this is a terrific paper, even though it's 16 years old. They were looking at the history of the photolithographic alignment equipment industry. So photolithographic alignment equipment is equipment that holds the mask on the silicone, essentially, or near the silicone for the etching process and the creation of chips. And there have been a number of generations of this kind of equipment, each one having sort of an architectural improvement over the previous one. In the first generation, the mask was held in contact with the chip. And the problem with this was that it frequently scratched and damaged the chips, and there was a very high reject rate. So the first improvement in this line of work was a equipment where it was called proximity mask. It was not put right on the silicone. It was just held parallel to and very near the silicone. So you give up a little bit of resolution, but you get a much lower reject rate. All right, now the interesting thing for our purposes here is that that's a relatively small change in photolithographic alignment equipment from the contact mask to the proximity mask. But it's an architectural change in the sense that it kind of changes the potential interfaces among parts of the system. So for example, when you have a proximity mask, anything that produces some kind of vibration, for example, now has a strong interface with the mask. Okay? And so designing a mask and a system for holding the mask stable is quite different. So even though the company which was the market leader for contact masks was the first to introduce a proximity mask, the company never successfully produced a really good piece of equipment that sold well in the marketplace. They were overtaken by their competitors, and they went out of business. So what's the lesson here? The analysis that Henderson and Clark do of 4 such changes in the history of this equipment, where each one had a similar result, the market leader either went out of business or became a minor player, was that the architecture of the product gets built into the organization. So that, for example, the communication pathways become stable around the interfaces. So I know who I have to talk to make certain decisions, and I talk to them habitually. If the architecture changes, then I suddenly need to talk to a slightly different set of people or more people. And what happened is people did not adjust to that, right? So that's why they never built a decent mask. Also, people acquire information filters. So you can't pay attention to everything that's going on in a sizable project. You have to learn what you can ignore and what you have to pay attention to. Well, if the architecture changes, that information filter is no longer tuned correctly, and you will start ignoring, or you will continue to ignore things that you now have to pay attention to that really make a difference. And so it was things like this kind of way that the architecture gets built into the structure of the organization that in each case was the cause for the downfall of the market leader at that time. So, in this work, we kind of hypothesize that knowledge-intensive activities in general will contain lots of dependencies that kind of shift over time, especially in software, where the software of architecture, or the architecture of software, varies a lot more than the architecture, say, of a car, right, over time. So we have to deal with this much more in software, and it seems likely that we have lots of fine-grained dependencies that may change quite a bit in software as compared to other fields. And it may help to design tools that support these rapidly shifting coordination needs. So if it's generally the case, as Henderson and Clark found, that people are not very good at changing their behavior to sort of recognize these new sets of dependencies, maybe some new kinds of tooling would help with that. All right, so now having kind of given the introduction and motivation for why we care about coordination requirements, I'll talk a little bit about how we actually measure coordination requirements. First, I'll describe just sort of in general the method, and then I will show you with some actual data how we actually did this for a software project. So the notion is that you can use a matrix in a very straightforward way to represent dependencies among tasks. Right? So you put in each cell a number that represents the extent to which one task depends on another task. And this is not real data. That's why you see zeros along the diagonal, which make absolutely no sense. But just go along with me here. So then you can also construct a matrix that shows task assignments. This is people by tasks. Okay, this person worked on this task, or this person did not work on this task. Okay. Now, what you get if you multiply these two matrices is you get a task by worker or task by person matrix that represents the extent to which this person worked on tasks that share dependencies with this task. Okay, that's what that matrix represents. And with one more manipulation here, we multiply this by the transpose of the task assignments matrix. We come up with a square matrix, people by people, that represents the extent to which this person works on tasks that share dependencies with the tasks worked on by this person. Okay, so this then would be sort of a task dependency matrix of the type that I described. This is the task dependency matrix. This is a coordination requirements matrix that shows which people need to coordinate with which other people in order to get that work done. Okay, I assume everyone here is familiar with basic software development tools. I probably don't need this slide here, but just talking about the kind of data that we're going to use now to actually construct a real one of these coordination requirements matrices. Archival data from a large software development project. This project, is a small company. They have one product, 114 developers. We have almost 3 years of data. They're grouped into 8 teams at 3 different locations. So that's the data we're using for this. They had a modification request system, which is used the way modification request systems are usually used. People request a change, and developers, if it's approved, go out and make the change. We picked all of the multi-component modification requests. So we just filtered out the simple ones that touched only one component. We're focusing only on the modification requests where more than one component was changed in order to implement the request. And the tool, the modification request system, has, as most do, a capability for asynchronous discussions. People could discuss the change. And then we also use data from the version control system, which, as you know, maintains all the changes to the files. And the developers also had access to and used IRC chat. Various teams had chat rooms set up, which they used quite a bit. All right, so that's the source of the data. Now, here's how we constructed a coordination requirements matrix using the data. So this is the task dependency matrix, right? It's a square matrix, files by files, right? And in each cell, we represent the number of times 2 files were changed in the same modification request, okay? Which we think is a good proxy for all the dependencies that exist between the stuff in those files. So if two files are changed together frequently, well, there's obviously some relationship between them, some dependencies between them, right? So that's our task dependency matrix. The task assignments are which developers modified which files, right? And you can compute this for any unit you like. You can compute this for, say, a particular modification request. So for one modification request, certain developers modified certain files. Or you can compute it for a period of time, a week or 2 weeks or whatever. Okay? So, and this is just the transpose of the task assignment matrix. And so you do this multiplication, and you come out with, again, a person by person or developer by developer matrix, which shows the extent to which one developer changed files that were related to the files changed by another developer for that period of time or for that modification request. Okay? So that's computing coordination requirements. One of the things we are interested in is the extent to which these are volatile. How much do they change over time? Okay, in other words, are people coordinating with the same people all the time? And are people coordinating exclusively with people on their own team from time to time? Or do they need to coordinate with people from their own team, from other teams from time to time? So what we're showing is in blue here, the diamonds. We're computing on a week-to-week basis the extent to which the set of people that you had to coordinate with changed from one week to the next. This is an average computed over all the developers. So if I need to coordinate with 10 people this week, and next week one of them changes, then that's a 10% change. Okay? So this is the average over all developers. And you can see this is from one release. This is from release 2, I believe. Release 3 and 4 look very similar. Release 1 is much lower, much less volatile, much less need to coordinate with outside people. So what the green is showing, the squares, that's what proportion of people that I need to coordinate with are outside of my own team. Okay, so what we're seeing here then is that early on, most of the coordination is strictly within teams, for about the first 10 weeks or so. And then over time, you start to see some churn as, there's the coordination requirements begin to change. It goes up to as high as, about 40%. But it's substantial throughout most of this period of time, and it is reduced again at the end. And the number of people outside the team that one needs to coordinate with, again, especially in this middle period, it's highly volatile and goes up as high as about 2/3 of the people that you need to coordinate with are actually people who are not on your team. So our expectation that coordination requirements are actually pretty volatile seems to be the case, that in software, the people you need to coordinate with week to week seems to change quite a bit. And the number of people that you need to communicate with on other teams also seems to be fairly substantial. All right, so those are the coordination requirements. Now let's talk about comparing the coordination that's required with the actual coordination that happens. Okay, so in the context of our data, we have about 4 different kinds of actual coordination matrices we can construct. So one is just team structure. So people are on the same team. They have meetings. They're usually, in this case, always co-located with each other at the same site. They talk to each other, you presume, fairly often. So we can, as sort of a proxy for all the things that team members typically do to communicate and coordinate with each other, we just note, we create a matrix representing who's on the same team. Okay, so there's a 1 there if they're on the same team and a 0 otherwise. So that is one form of actual coordination or proxy for team-oriented kinds of coordination. Geographic location, similarly, people at the same site run into each other, talk to each other a lot more. There's lots and lots of evidence showing that communication is far more frequent when people are at the same site than when they have to use a phone or email or something. So again, we can represent that as another matrix, person-by-person matrix. Use of chat. So in this case, we looked at the IRC logs, and we had actually 3 people who were members of this organization looking at the IRC logs and identifying when a particular change request was noted in the logs and who participated in the discussion of that change request. So we can say for each change request, whether people who talked with whom about that change request in IRC. And that's the matrix that we construct here. And finally, we have bug discussions, online discussions in the modification request system. Again, similarly, for each change request, who actually participated in that discussion. Those who participated get a 1; those who didn't get a 0. Okay, so that's what I'm talking about when I'm talking about actual coordination or coordination behaviors. It's these 4 matrices over here that are empirical observations that have nothing to do with the way we computed the coordination requirements.
What about things like work structure? So is that fit within team structure, or is that something different?
Work structure, so can you say a little bit more about what you mean?
Breaking down the work, right, and illustrating coordination. Like, you've got a scenario or something like that, and you're breaking it down into a list of features. So, that's a work structure.
Right. Well, the only work structure that I think that is kind of related to this is just the basic division of the work of designing and developing components. So it was always the case that they assigned development of a component to a single team. So there was never, a case where they assigned a component to multiple teams. But we aren't actually looking at, what the work packages or units were. What we're looking at in the results I'm going to show you is the unit of analysis is actually the modification request. So what we're doing is we computed coordination requirements matrices and actual coordination matrices of these 4 kinds for all the modification requests that touched more than one component. So that's going to be our unit of analysis. We're going to look at that whole set of modification requests. Okay, so what I should have said here is then it's very straightforward to compare these 2 matrices and get some measure of how close or how far apart they are. There are a number of ways one could do that. The way we did it is to look at every cell over here that's non-zero, okay? And for each of those non-zero cells, we look over here and see how many of that set of cells is also non-zero. Right, so the set of cells that are non-zero over here is showing us who ought to coordinate with whom. That's what we're claiming. And over here, looking at that subset of cells, which proportion shows actual coordination? Right, that's the measure we're calling congruence, the extent to which all the coordination that should happen actually does happen. Since it's a proportion, it's between 0. If none of the people who should coordinate actually do, then it would be 0. If all of them do, then it would be a 1. So it's a number that varies between 0 and 1. All right, so now we're going to take a look at the effects of congruence on development speed by looking at the amount of time it takes to actually implement the change for the modification request. So the unit of analysis is the modification request. There's 1,983 of them, just to give you an idea of the size of the data set, that were implemented over a period of about 3 years, a little bit less than 3 years. So we constructed 4 measures of congruence, once for each of the 4 kinds of coordination behavior that I mentioned in the previous slide. And then we constructed a regression model, right, using congruence and some control variables as predictors, right, trying to predict the resolution time for a modification request. Right, so we want to see if the congruence has significant impact on how long it takes to do the work of resolving the modification request. So here are the regression results. I just wanted to put the full model up there to point out that you have to have a lot of control variables to help explain the variance in a regression model. We had a number of variables to account for things like, on how many other modification requests was this modification request dependent. We have the priority was a 1 through 5 assigned by management. How many times was it reassigned to a different developer? Because that's going to affect the amount of time. Every time it's reassigned, the new person has to get up to speed. Was it a customer modification request or one that was found that originated internally? Which release was it? Kind of a proxy for changes that might happen over time. Team load, that's just how many modification requests was this team working on simultaneously divided by the size of the team. Some sense of how loaded was this team at the time. The average programming experience of the set of people who worked on it. How long people had been in the company, how much experience they had with that component. Okay, so the notion is that if you've used regression modeling, you really want to get a good set of control variables to not leave a lot of variance unexplained. And so these are just our control variables. We don't really care that much about the outcome, but the outcomes did look kind of as you would expect for all those variables. Now here are the ones that we really care about in the model, the congruence predictors. And we can see that all of them were statistically significant. Now the reason we have the models arrayed like this, model 1 is the control variables only. Model 2 is we added in the predictors we really care about, the congruence variables. This data set has only 809 cases because we couldn't get the insiders to code up all of the modification, or all of the chats for all the modification requests. It takes too much time. They coded up 809 for us, randomly selected. So we had a smaller data set looking at IRC congruence. For the full data set, we have essentially the same results, except that we didn't have the IRC coded. No one had gone through to look for the rest of them which bug the discussions were related to. But it does confirm our predictions. These are the essential kind of important results that each of these kinds of congruence helps to shorten up the development interval. And interestingly, none of them were significantly correlated with each other. They seem to be sort of independent effects, if you will. All right, so just to summarize from that last table, the time to complete the work item, the modification request, was reduced by each of the 4 types of congruence: being on the same team, being at the same site, chatting together with other people involved in the work, or being involved in online discussion. Okay, so another thing we want to look at is how does congruence evolve over time? I mean, are people, instantly at the high level of congruence, or does it get better over time? Does it get worse over time? How does it evolve? So we looked at the data from the first 4 releases of the product. For this data, we computed congruence on a weekly basis instead of on a per MR basis. So for each week, for that about 3-year period, we measured all 4 kinds of congruence to see how they changed over time. So the analysis showed there was a significant effect of time on the various measures of congruence. Again, we did some statistical modeling to show that. I won't show you all the details. The pattern of communication between the top performers and other performers was one of the more interesting things here. So here's kind of the evolution of congruence. So let me interpret this a little bit for you. So what this is, these are the 4 releases of the product. And what we're looking here is just what was the level of congruence for each release, the average level of congruence. And we find that you start out and geography and team structure are very congruent. So that means the work was assigned in such a way, right, that you only had dependencies with other people on your team and at your site. Right? There's really no need to coordinate with anybody else. Right? This is kind of this was actually the explicit design intent of the way the project was set up, was to assign a component to each team And hopefully, most of the coordination will just be within teams. We won't need a lot of coordination across teams. So for the first release, that's exactly what seems to have happened. And whatever communication there was in the bug discussions and in IRC had no relationship to the actual work that was going on during that period of time. It was not congruent. Okay. But then we see things starting to change. In Release 2, modification requests and IRC discussions are becoming much more congruent than they were previously. And we're seeing that all of a sudden you have to start coordinating with people who are not on your team, right? Which wasn't true earlier. By the time you get to Release 3, being a member of the same team isn't really telling you much about who you have to coordinate with, right? A lot of the coordination, more than half of it actually, is with people on other teams. And the use of IRC and chat becomes highly congruent. So there's probably a lot of reasons for this. One reasonable interpretation, I think, is that when you start developing the components, you're building kind of the basic functionality of the components in Release 1. And Release 2, 3, and 4, you're worrying more about how they function together to implement functionality. There's a lot more cross-team and cross-component kinds of dependencies. And so despite the best intentions to reduce the need to communicate as much as possible across teams and across sites, you end up needing to communicate with people on other teams. There's also a lot of evidence that even for something that's architected very well at the beginning, over time you start having to make changes that weren't precisely anticipated by the architecture, and they tend to be more and more cross-cutting over time. And that's what we seem to be seeing here. So one of the possible conclusions of this is simply that no matter how well you match up the organization and the architecture of the software, that over time the match is going to become less and less perfect. You either have to re-architect, refactor the software, or you have to reorganize, or you have to be prepared to support collaboration across teams and across sites. But you're going to need to do one of those. Okay, then some of the results that you may have seen before have to do with the relative productivity of different developers. There's been a lot of research on this, and there's a major difference in the productivity of the most productive and less productive developers. And we're just sort of confirming that. This is the same finding that everybody else has found that's looked into it. But in this particular case, what we're seeing is there were 114 developers. In this particular case, 18 developers wrote half the code. So it varies a little bit from one release to the next. These are cumulative contribution curves where you order the people from the person who wrote the most code to the one who wrote the least code. And then you simply create a line showing what proportion of the total has been accounted for. It's a cumulative curve. And so you can see that if you average across the 4 releases, it's right about 18 developers have written about 50% of the code. So we thought it would be interesting to see if those 18 looked any different from the rest. Now here's what we see if we go back looking at the average level of congruence for the 18 top developers. We kind of see a pattern that looks vaguely like the total pattern did, although things are kind of shifted upward a bit. They start out being pretty congruent in IRC right from the beginning, and the team structure comes down as it did in the other diagram. If we look at the other 96 developers, we see that they really never achieve very high levels of congruence in their communication. So it starts out very low and stays pretty low throughout. So I don't know, it's hard to know exactly what this means, but usually when people talk about this difference between highly productive and less productive developers, it's assumed that it's some sort of innate ability that they just write code really fast, and maybe that has a lot to do with it. But what this kind of suggests, at least, is there may be kind of a social component to this ability to be very productive, that people who really sort of understand the system, understand who is working on what, and make sure that what they're doing fits with what somebody else is doing, it's at least something that's highly associated with productivity. We don't know what the causal relationship is, but it certainly is highly associated with being very productive. This is sort of opposite of the popular image of the nerd sitting in the office never talking to anybody, just hacking out code. It doesn't seem to, these data seem to show that it perhaps doesn't work quite like that. And there's also other interesting research done by people like Tom Allen at MIT showing that the top performers tend to have more contacts outside of their immediate group than everybody else. And this sort of fits with the picture that's created by some of this previous research. Okay, so implications for distributed teams. The coordination requirements seem to be pretty volatile. So if it is true in software development, as it seems to be true for lots of other areas like photolithographic alignment equipment, that people aren't naturally and kind of automatically aware of the changes in coordination requirements, that it's difficult to know the full extent of the dependencies of your current work with other people's work, then software development is particularly difficult in that regard because of this volatility. Congruence has important effects. It shortens resolution time. This really has convinced us that this is kind of a meaningful measure because it shows that time is reduced where congruence is high. And also the very top performers tend to behave very congruently. This is kind of fairly convincing, I think, that this congruence is it's a decent measure of congruence, and it's something that's important in actually getting the work done. So what does it say about things like awareness tools? Right now, for example, IM tends to have kind of self-selected buddy lists, which don't change all that much. I guess they change to some extent, but you don't change your buddy list every week typically. So if it's the fact that in work, the people whose work depends on yours and vice versa changes quite a bit, and people tend not to be aware of all who those people are, it suggests that you want some other kind of mechanism for automatically noting dependencies rather than just relying on people to try to figure out who they might want to be aware of or who they might want to chat with or who their work affects. It's also not just the members of the same team, so something like a team chat room isn't really going to take care of the right, getting the right set of people together either. So one can imagine tools that are based on the current set of task dependencies. So you start looking at a couple of files, for example. You could imagine just in the background doing this computation saying, okay, you're moving into territory where these three people are doing a lot of work. Before you check something in, maybe you should at least sort of see what they're doing and consult with them or get a quick look at the work that you've done, especially if you see unfamiliar people there and you don't know what their role was. This would be a clue that, gee, maybe I better, take a look here. And so I'm arguing also that there's a huge potential win for software as a service here. So here's where there's kind of a leap. This is a leap towards a research area that I'm very interested in getting into. So as I mentioned at the beginning, you can see now what I meant, I guess, when I said that this rich history of all the work and how it was done, who was involved, what depends on what, is created sort of automatically by the kinds of tools that we use in software. And it makes it possible to compute some really interesting stuff about whose work depends on who. And we could imagine, in fact, creating even richer data sets by capturing more of what people do online, which is something one of my students is working on. But if we were using tools, as you typically would if you were delivering software as a service, where all the data sits centrally, you can put it in whatever form you want it. You can save every version of everything. You could note the sequence in which people work on different documents, right? So that they look at this spreadsheet and they go to this Word document and they do something else. There's all sorts of information about the work and how it gets done, who did what, that one could capture in a very straightforward way. That would make it possible to do, I think, all sorts of interesting things in terms of providing collaborative services. So you'd want to capture all versions of all documents, who changed it, what was the change, when was the change made. You would want something like session data so that you would know that, if I'm working on using a spreadsheet, I'm using this word processor, using this and that, looking at email, if we could sort of have some sense of a session, then it would tell me that those things are all related. If I go away for an hour and come back, start doing something else, then there's sort of a break, and that stuff is not necessarily related to this stuff. That's sort of what a modification request does for us in software. Right? So you want some way of understanding, what belongs to one task or one session. That would help to understand the dependencies. So the kinds of tools that you could hope to get are things like a content history. So imagine something like a great big project proposal, 400 pages of proposal that was written by lots of people over lots of time. It's maybe evolved from previous proposals and so on. You can imagine having a very detailed content history where you go, okay, here's some text, here's a graph showing some data. Where'd that come from? Okay, now I can go back and look at the spreadsheet where that came from. I know who put it there. I can go see the data where it came from. Where were the data imported from? I can maybe go back and see where the data were imported from, who gathered it. I could find all sorts of things about, I could do sort of archaeology of the document, telling me a lot about how much I should believe certain things, about, how current the data is, about do I want to just, grab this graph and paste it into something new, or, I could investigate whether it's really appropriate to do that. There's all sorts of things that would be possible. I know how to contact the person who made this particular change to the data that changed the graph, and I could ask them about it. So you can imagine all sorts of possibilities for kind of collaboration based on capturing that rich sort of data. You could also imagine, as I discussed a little bit for software, an awareness based on coordination requirements. Based on the past history of this set of documents, if I change this spreadsheet, who's going to be affected by that? Right? Right now, that's with different applications on different computers and different files and no history of versions. You don't know any of that stuff. It's very hard to tell. Comparing coordination requirements and behavior. One of the things we're talking about also is, you can imagine in software, for example, a very useful management tool that would every week, every 2 weeks, would compare what are the coordination requirements for this period of time, who should be coordinating with whom, and then making sure that they actually are, if they need to. Or maybe you could marry it, as we're starting to do. We're experimenting with constructing social networks. And because all these matrices are basically networks represented in a slightly different way. So you can imagine comparing the coordination requirements network with the actual communication network for that period of time, or the social network, and seeing if they're actually congruent. If the coordination requirements change suddenly in a way that people who don't know each other, haven't communicated much in the past, need to communicate, then as a manager you want to step in and make sure that's happening, which could presumably head off a lot of problems with things like integration later on. Okay, and that's it. So we're actually looking for application areas to work on and collaborators. I have a student who's very anxious to kind of move into this area and move beyond software. Okay, that's it. Thank you very much. I think we have time for questions. Gina.
So here at Microsoft, for example, so you talked about how the org chart, how the physical arrangement, and then how the computer-mediated communication differ with respect to congruence. And at Microsoft, we have very stable org chart at the end of the release. Then the other shuffle, and fairly stable physical locations for people, and of course all the electronic flexibility you could want. Whereas in Agile, they're trying to break down both the physical and org chart boundaries, and in the open source community, there is no physical co-location, and there is no org chart. So in those two, it pushes way more towards a much more fluid, much less viscous realm of computer mediated communication. So how do we get some of that? I want some of that stuff.
Well, so there's a lot of literature in organizational behavior that suggests that if you were designing an organization, that the stability of the environment is a crucial variable. So if you're designing an organization for a stable environment, then bureaucracy makes an awful lot of sense. So it makes sense to have a central purchasing department because stable environments, you're always buying, 12-inch red widgets. Okay, so they can take the time and look over all the manufacturers of 12-inch red widgets, find the best and cheapest deal, and then put in place a rule that says everybody buys 12-inch red widgets over here, right? So centralization makes a lot of sense when the environment is stable. When the environment's unstable, this week we need 6-inch blue widgets, and next week we need something else, and the week after we need something else. Trying to have that kind of centralization is a disaster because the need to shoot information around the organization and so on is just overwhelms the communication channels. So decisions have to be pushed down more locally. Okay. So to me, this is very much like the difference between an organization that's building something with a very consistent architecture, right, where things aren't, you may be evolving it, but the structure stays stable. It makes sense to make a lot of architectural decisions centrally, then enforce them, and so on, versus the agile approach that may be more suited to a very unstable environment where you have no idea often exactly what you're going to build. You only can build little pieces of functionality because that's all you understand at one time, and you need to put it into place and get feedback. So I see these organizational things as being a response to some extent to uncertainty. So I think part of what we're seeing with the coordination requirements, I would guess, any real computation of coordination requirements has not only to do with the interfaces and actual dependencies in the code between two components, say, right? If we're building two different components that interact in certain ways, the ways that we have to interact depends not just on the nature of the way the components interact, but how certain we are about that, right? So if they interact in really complex ways, but we both understand this protocol really, really well, we just build it, right? But if we think they're going to interact in simple ways, but we're not really sure, we're constantly checking back, we're constantly negotiating, talking, is this going to work, is that going to work? That's a much more difficult coordination problem. So I think the coordination requirements, this is just sort of a start, what we've got here. There are many things that impact coordination requirements beyond this. And I think the certainty is a big part of that. So I'm not sure how you get that into Microsoft except to make your environment much more unstable, which may or may not actually enjoy it.
So it seems like there's two different approaches. You can either try to get the actual coordination to try to get more congruent with the required coordination, which is talking about making Microsoft more agile. Or you could do the other way around. You could make the required coordination less. Or you can make the required coordination match more of the actual coordination.
Yep.
So I think that route is more interesting. To me, the real problem is that we take on all these dependencies on other people, other groups, other components, and a lot of times these dependencies are taken on without even realizing it.
Yeah.
And the entire underneath it, there's this underlying network that's being created without our fully being aware of that. And one thing they've done at Microsoft is that they now explicitly check that if you try to go from one layer of the architecture to a higher layer, that it flags that. So even though people aren't even aware that they're making a dependency, it'll tell them, we don't want you to make a dependency in this direction. But maybe we need more tools that'll tell us things like that. Do you realize you just made a dependency on a group in, India that, it's very far away, very hard to coordinate. Are you sure you want to take on that dependency?
Yeah, I agree. So there are a couple things that I think are potentially important. One is I think what you were sort of hinting towards, that you want to have a match between the organization and the architecture. And understanding the details of what that ought to be, what that means, I think is important. And I think tools may have a big role to play there. So the other thing, though, is sort of the question of what do you know when in terms of time. So there's a lot of kind of religious debate between people who are heavy process people and people who are agile, for example, or people who are heavy architecture people and people who are agile, right? So they debated as if it was always right either to do a lot of architecture work up front and then just stick to it, and then to do lots of heavyweight process stuff and enforce the process. Whereas in fact, I think the appropriate point on those continua has an awful lot to do with the nature of the project. So if you know and are sure, because you've built 10 of them before, that this is the right architecture, design the architecture and make everybody stick to it, right? But if we're building something where, we have some users trying to help us out, they don't really know what we want, we've never built one before, we don't have really much of a clue as to what the architecture is going to look like, then if you go build an architecture, you're just wasting your time, right? So I think that's true kind of on a process dimension, on an architecture dimension, once you know what the architecture should look like, then you can have tools that will enforce that, that will look over the rules and say, no, you want to look at this because we know that's not a good idea. So I think there's a couple things operating, the stability environment, how much you understand at what point, and you have to take an approach that's appropriate.
Also the software construction tools that we have. I mean, a lot of these dependencies arise just because we can't handle cross-cutting concerns very well. I mean, we take on these dependencies and maybe if we had better software tools we wouldn't even have.
Mm-hmm. Yep, that's a very good point. Tools may, they already are playing a big role here, and they'll play more as we go along, the more we understand it. But I think we're talking about maybe two different kinds. One that sort of enforces the rules when you know what they should be, and others that help you, that help you coordinate with the right people when you don't know what the rules should be, but you know who you might screw up, right? I mean, I think we need a continuum of tools as well. I think they'd be helpful in all those areas. Yeah?
So you mentioned a few times that people might not be aware of what their coordination requirements are. And I guess I don't know of any evidence that tells us whether or not they do, or whether good ones know it better than bad ones, or how that varies between organizations. Do you know of anything that says there's a big group of developers that just don't know who they should be talking to, or is it?
So there's not a lot of evidence from software. There are papers in other product development fields, like the Henderson and Clark paper I talked about, which shows that, at least under some circumstances, people seem unable to find the right set of people to talk to, particularly when there's an architectural change. And then I think, at least from this work, there's some evidence showing that the top performers, communicate in a very congruent way, and the lesser performers communicate in a much less congruent way. I think there are a few bits and pieces of evidence. I wouldn't say that it's absolutely established at this point, but there seem to be hints from multiple places that it's pretty tough to tell what the full impact of some change that you make might be, especially when the change has some architectural implications. Yes?
So in the data you presented about the good performers versus the lesser performers in the software team, the good performers were correlated with high sociability over IRC chat.
Well, we don't know if they're social or not. We just know that they were talking to the people that we thought they should be talking to. Yeah.
So, are there any other data points saying what happens if you just make a software team just of those 18 people, whether they'll be as efficient, or do you need the other 90% of the lesser people to do local things that don't require either don't require lots of communication, or maybe they just need to be there as to make the 10% feel better about themselves and work harder.
Well, so not from this study, but there is research that sort of looks at this. So one example would be Tom Allen. Again, I mentioned him earlier. He did research on what he called gatekeepers in engineering organizations. And it turns out he was interested in the question, how does new information, new technical information and techniques find its way into an engineering organization? And this is against the background of surveys that have been done up to that point that show engineers don't read papers. Almost, the rate of readership among engineers of papers, technical papers, is very low. So people are going, well, how can that be? Are they all just aging and going to be no good? Or how do new ideas ever come in? It's a terrible situation. Maybe we got to lash them into reading more papers. But he sort of looked at how information actually flows in engineering organizations. And it turns out there's sort of a small number of people that he called gatekeepers that read lots of papers, actually. And they write papers, and they go to conferences, and they have contacts outside of their own group, both outside the company and in other groups in the company. And the way information typically flows is when people, when these gatekeepers find out new things that are relevant, they go show people and talk to them about it. Or when people have questions about, gee, I wonder if there's any newer technique for doing this, they would come to the gatekeeper who uses his knowledge of literature to help answer the questions. The other thing that was interesting is when you look at the social networks of people, the gatekeepers are almost always in the same network, most of them anyway. So not only do they bring in information from the outside, but they talk to each other. So it seems to be the case that they're like the nervous system, if you will, for new information getting into and circulating around the company. So they not only are aware externally of more people and more ideas, but they also know what the other gatekeepers know and what they keep up with. And so they can provide one source to access lots of information inside the company. So one guess or one interpretation, we don't really know if these people are also gatekeepers. And by the way, the gatekeepers also were technically highly regarded people and very productive as well. But one possibility might be we've just found the gatekeepers here, and that people just communicate with them for particularly relevant kinds of problems, and they supply answers. We don't know who's initiating the communication. It could be they are asking questions, they're disseminating. We haven't looked at that. But so there are suggestions about the relationship of these people and everybody else, that they all work together to get the work done. But this information dissemination function seems to be handled by these communities of gatekeepers. Yeah.
You study data from other global companies, such as, for example, service providers or others that have a global supply chain across the world, and Infosys or any of those companies, for example?
I spent about 6 years in Bell Labs, so I studied lots of development groups at Lucent. And since I've been at CMU, I've studied development groups in several other companies. But we haven't done this exact study with any company except for this one. We're trying now to get data to replicate it at a few other places. But that's it for the moment. Yeah.
Do you have any insight from your data about coordination that takes place between developers and the non-developer roles? Say between developers and testers, what format that takes place?
Yeah, no, that's a great question, and we don't have any data for that. I'd like to, and we plan to sort of expand this beyond just the development group. So this is sort of an initial cut looking just at coding, but there's all sorts of dependencies on design and requirements and marketing and product management and maybe even customers and testers and all sorts of things that are probably equally important. But this was the data we had access to. This is as far as we've gotten at the moment.
Some of your ideas here for these tools ideas, content history, and this idea about sessions that you were talking about would start to capture that a little. Because you'll maybe see some relationships between documents outside of code documents and sort of pick up on that and use that.
Yep. One of my students is working on a project where he is building an Eclipse plugin. The first step to the project is building an Eclipse plugin that captures very detailed data about everything a developer does that could be captured in that environment. So every file that's opened and where in the file they look, and the scrolling around in the file, and opening a web page, looking at documentation, everything that a developer does that can be captured, pretty much he's capturing. And the idea then is to use that to sort of create a history for every change. So the notion is I could look, if I wonder why does this function look this way, I would expect it to look some other way. I can sort of click on that, and it would pull up sort of replay of everything that happened up to that change that this developer did. What documents they looked at, what files I had opened, where they were looking in those files, and then finally the edit. And hopefully from that kind of recreation, that replay, I could figure out why it looks the way it does. So I guess, yeah, I think you're right that we should be looking for more ways to use data that exists, but I think we can also start capturing more. And there's an awful lot that could be recorded if we designed our environments to do that. And I think a lot of it would be useful. We'll sort it out. Some of it probably won't be. But we need to find ways of capturing it and then ways of filtering it and displaying it so that you can actually get something out of it. He's an Eclipse junkie, sorry. Yeah.
In Release 3 and Release 4, you showed the congruence of the org chart increasing. And you suggested that there could have been a better org chart. Is that true? That there's an optimal org chart given the communication that is happening among this group, or is it really that the network has gone scale free or something?
Good question. Yeah, I don't know. That's something that we should look at, though.
It seems like you're saying that the developers that are the top performers don't really care what the org chart is anymore. But the ones that aren't top performers, it's very important to them to have a team structure that matches the requirements.
Right. Yeah. So it could be. So yeah, if we have this sort of Tom Allen-like gatekeeper structure, then I think what you said is true. And your suggestion that there is no perfect org chart is also true. That you just have to get used to the idea that the thing is a big network and it takes its own shape, and you don't want to take all the gatekeepers and separate them, so they don't communicate with anybody. That would be just stupid. So it may well be that we need to think about organizational structure not as an org chart, but as a network. Maybe the org chart and the tree or the graph or whatever is, the tree is just a wrong model. And even a matrix one may not be interlinked enough. So I don't know how you adjust sort of authority and responsibilities and so on in a purely network structure, but it certainly seems that, based on previous work, that's likely what we would find. We plan to do that analysis. So it's the same question you could ask about the volatility question. So if my volatility is 20% for several weeks in a row, does that mean that there's just, say, a few people that are flipping in and out, the same people over and over again, which would show up as volatility, or is it this two people, now a different two people, now a different two people, now a different two people? We haven't looked at that. I don't know which of those it is. So there's more to be done there. I suspect it's kind of a network-looking thing, and I suspect you probably can't have a good org chart.
Well, is it a network that has local connectivity, like a network of roads between cities, or is it a network that has that's scale-free, where you have some links that are going like a
small world. Yeah. Well, my guess would be so the gatekeeper networks you would expect are kind of small world type networks, right, which have high clustering but also short average distance, right? So those are the two characteristics that together make kind of a small world network. So that I'm tightly linked to my group, and we're separate from other groups, but there are enough random links among clusters that the average path between any two people is short. That's what this gatekeeper, since they talk to each other, they create these links, among clusters. That's the sort of network they would produce. And I suspect that we'd find the same here, but again, this is something we haven't looked at yet. But I imagine that's how it works, a small world kind of thing. Yeah.
Can you give us information about the top 18 contributors?
So what about the
geographical information about the top 18 contributors?
Oh, where they were?
Yeah, more structure. I don't see that dimension at all.
Yeah, that's true. So you see that for both of them, geography remains, kind of high in congruence. In other words, that they usually just have to coordinate with people at their own site, but often with people on other teams. So that would lead me to suspect the software is kind of hierarchically structured, that the components are somewhat separate from each other, but they're more closely related to components developed at the same site and less related to components at other sites because there doesn't seem to be this cross-site congruence happening. But it could be, the cause could be the other way too, that they realize, well, we'll never be able to coordinate across sites, so we're going to, we're not going to do that. We're going to have some nice separation of things. But yeah, I don't know where the high performers were. I know they were not all at one site. They were spread around to some degree, but I'm not sure how evenly. Yeah. Any other questions?
Well, let's thank Jim one more time.